Okay, so today we're going to start kind of a brand new topic. We will be using some of the things that we talked about when we discussed linear functions, but it's really kind of a standalone topic. And we'll be on something involving this really for the rest of the week. So we're going to look at systems of linear equations with two variables. Let me see if I can get that a little more focused. Well, that is not more focused. All right, that's about as good as we can get it. All right, so first let's talk about what a system of equations is. So notice that equations is plural, and so basically it's a set of multiple equations with the same variables that work together to describe a scenario. In this class, we tend to stick with only 2 or 3 variables, but just know that these can be a lot more complicated than that. But they're not standalone functions. They're functions that work together, and so a solution to a system is a point or an XY partnership if it's 2 variables that work for both equations. So another way to say that is it's the intersection point or points of each equation in the system. Okay, it's what they have in common. And so here's what system of equations are going to look like. Kind of like when we talked about piecewise functions, we use a curly brace to indicate that the following things are grouped together in some way. We just don't have something out to the left this time. So you might see like 2x plus y equals 7 and 5x plus 6y equals 8. Okay, so notice that's a set of 2 equations using the same 2 variables, x and y. Okay. So to find a solution for this, we would need to find an XY pair that worked for both equations. Okay, that when you plugged it into the first one, you got 7 for an answer. When you plugged them into the second one, you got 8 for an answer. Okay. So we have many different ways of solving these in algebra. And the list I'm about to give you is only the types of methods we're going to look at in here. Actually, there's more than what I'm about to list for you. That if you took regular algebra, you would be going over a little bit more of this. So the first method is called the elimination method. Some textbooks call it the addition method. And the second method is called the substitution method. The name implies what we'll be doing. So in the first method, we will be adding equations together and it will eliminate something. In the substitution method, we'll be substituting something in for something else. And the third format is the graphing method. And by the way, this is actually a topic we're going to hit later on in the semester towards the end as well. So we're just kind of introducing it here, and we'll bring it back up when necessary. And then the fourth way is through the form of a matrix. The plural form of matrix is matrices. So I'm going to kind of demonstrate all of these methods. I'm not sure we'll get to matrices today, but we are going to get to matrices. So if you don't know what those are, / you've always had a little bit of a hard time with them, we're going to work on those. So let's say that I asked you to solve this using the elimination method. Okay. The elimination method probably should be something that you've seen before, just because all Algebra 1 classes pretty much across the world pretty much cover system of equations in some way, and elimination/addition is probably the most popular method of solving these things. Okay, so in the elimination/addition method, we're going to try to add the equations together and eliminate something. Okay, so here's the gist of the elimination/addition method. You're going to multiply 1 or possibly both equations by a constant so that when the two equations are added together, one variable gets eliminated. So note, that is why some books call it the addition method and some books call it the elimination method, because you're going to be adding equations together and one of them is going to get eliminated. So remember, in algebra we can only add what kind of terms together? Only like terms together. So if you added up like terms, notice if you added it here and here, you would not get an elimination, right? This would be 3x and this would just be y. Okay, so the point is we want to multiply one or both of the equations by something so that when you do add them together, one of them will go away. Okay, so notice this is already negative and this is already positive. So what would I really like this to be so that it would cancel with this plus 2 and would get eliminated like I want? What would I really like the number in front of y to be? 2, in fact a negative 2, right, and it's already negative. So I'm going to multiply the first equation by 2. I'm allowed to do anything that I want as long as I do the same thing to both sides. So this is essentially what I get. I get 4x minus 2y equals 16. Make sure you double everything, so it's not just 2 times the y term, it's 2 times everything. Okay, and then we're going to line that up with the second equation. But now notice if we were to add them together, what's going to happen with the y's, just like the name of the method implies? It's going to get eliminated / canceled, right? So we're going to get 5x equals 25. Okay, but then I think we know what to do here, right? What do we do? If we want y, what do we do? Divide by 5. So it looks like we get x equals 5. Okay, so that is half of my answer. Oh, let me move that up. Sorry about that. But my answer should be the point that they have in common, an x comma y. So how do you always find the y once you know the x? Plug it in, right? So now we're going to find the y by plugging in x equals 5. And so you may ask yourself, which equation should I use? And the answer is it shouldn't matter, because remember, an answer to a system is supposed to work for both, okay? So I would go back up to my original equations and I would pick the simplest one. Which one looks simpler? 2x minus y equals 8 or x plus 2y equals 9? Probably the one that's all positive, right? But it wouldn't matter one way or the other. So I'm going to choose x plus 2y equals 9, and I'm going to replace that x with a 5. And then I'm just going to see what I get for y. So I'm going to subtract 5 from both sides. So I get 2y equals 4. Divide both sides by 2. So what does it look like y is? Y is 2. Okay. So my answer then is the point 5 comma 2. Okay. And you can check this by plugging it into both equations. And that's a really great way to check because it has to work for both. Okay, so as you're just kind of getting started here, if you're not quite sure, did I do something right? You can use a calculator or something and plug it in for both. Okay, so we're going to do that real quick. I'm not going to write it down. We're just going to plug it into our calculator. Let's see if I can get it to not be glary. Okay, so I'm going to take the 5 comma 2 that I have here and I'm going to plug it into both of these. Okay, so 2 times 5 minus 2. Okay, so I'm plugging it into this equation. What should I get if I did it right? What should be my answer for 2 times 5 minus 2? Should be 8, right? Notice that it is, and then I'll check the second one too. What should I plug in for this one? 5 plus what? plus 2 times 2, and I should get 9, and notice that I do. Okay? So as long as you check it with both, then you're good to go. So basically what this means is these two lines would intersect at what common point? 5, 2. Okay? So that's like visibly or graphically what it means. Okay, so that is addition/elimination. Okay, note the name implies what you'll be doing, right? We added equations together in order to eliminate something. Okay, so let's look at substitution. So I want you to solve this system, y equals 2x plus 1, and then 2x minus 3y equals negative 7. But I want you to use substitution for this. And I can't spell substitution, apparently. Substitution. All right, that looks better. All right, so how we do substitution is you basically solve for one of the variables in one of the equations. In other words, you make it look like either x equals or y equals. And then you're going to plug that equation into the other, into the second equation. So you make one of the equations look like x equals or y equals, and then you stick it in or substitute it into the other. Okay, notice that's already kind of done for us here, right? At least started for us. Because what do we already notice? One of the equations already looks like what? Y equals, okay? So all you're going to do is you're going to substitute in for this other y, and you're going to substitute that entire equation in for y. In other words, if y equals 2x plus 1, then let's substitute it in for the other equation, okay? So let's go ahead and write the second equation, and then we'll do our substitution step. So here was our second equation. Okay, so I'm going to substitute, bless you, 2x plus 1 in for y, but notice everything else stayed the same. Okay, so I did 2x minus 3 times the parentheses equals negative 7. So all I did was pull out y and substitute in what y was equal to. But then I can kind of clean up what I've got here. So I've got 2x minus 6x minus 3 equals negative 7. Make sure that negative 3 goes to both things, right? Negative 3 times 2x would be negative 6x, and then negative 3 times 1 would be negative 3. And then let's add like terms. So we've got negative 4x minus 3 equals negative 7. Notice what happened. I went from 2 variables to how many now? Only 1. So just like the previous method, I'm going to be able to find out what that one variable is and use that to find the last one. So I'm going to add 3 to both sides. So I get negative 4x equals negative 4. And then what? If I want x, what do I need to divide by? Right. Well, divide by negative 4, right? So we would get positive x. So we end up getting x equals 1. Okay. But now I still need to find what? Still need to find y. But I'll do that by plugging in x equals 1. Okay, so again, it does not matter which one you use. Okay, which one would be a little nicer if I'm trying to find y, though? Yeah, there's already one that says y equals, so let's just use that one, right? So here's y equals 2x plus 1 from the problem above. So let's just plug it in. So 2 times 1 plus 1 would be what my y is. Okay, so then the solution is what? Yeah, the solution is 1, 3. Now, in both of these examples, I ended up finding x first and then use that to find y. But if you find y first, what will you do with the y? If you plug it in to find which one? To find x. Okay, so just make sure that when you write your solution, though, that it's always x comma y. It doesn't matter which one you found first. X has to come first. Okay, so let's look at the graphing method. So I want you to solve y equals 2x plus 1. Let's do the same equation, and then 2x minus 3y equals negative 7 by graphing. I definitely want to cover this one because later on throughout the semester we're going to need to know how to do basic graphing and basic solving system of equations by graphing. Okay, so for this method, you're just going to graph both lines because they are both linear, right? They're both x to the first power equations. Okay, you're going to graph both lines, and what will you be looking for? Yes, okay, and look for where they intersect each other. Okay, so let's think about that for a minute. Most of the time they're going to intersect each other once, okay? Is it possible that they may never intersect each other? What kind of lines don't ever intersect? Parallel lines. So it is possible that they won't intersect, okay, but you'll just have to kind of graph it and see what happens. Okay, so I'm going to use kind of some different colors here in order to graph, but let's do a graph and go out maybe 5 in every direction, and then we'll go out more if we need to. Notice the first equation's already kind of set up for me to graph it, right? Like it already looks like y equals 2x plus 1, okay? So what did we say the method was for graphing lines when we had it in y equals form? You graph the what first? The y-intercept first, right? So I'm going to make it kind of large there, and then you count the slope from there. What's the slope if it's 2? How else can we kind of think of 2? 2 over 1, right? So that means go up 2 and what? To the right 1. So up 2 to the right 1, and we have this line. Okay, so I'm just going to call this one equation 1. Okay, but I still need to graph equation 2, okay? But what do you notice about equation 2? Yeah, it doesn't really look like we would prefer it, right? It doesn't look like y equals, okay? So it's 2x minus 3y equals negative 7. So we have two ways we can graph this. We can either look at where the x and y intercepts are, or we can make it look like y equals, okay? So I'll probably make it look like y equals just because that's usually the traditional way to solve this. So if you subtract 2x from both sides, if I'm trying to isolate y, then you get this. Notice I reordered it, right? We usually write the x part first. Okay, and then what would we do? I don't really want the negative 3y, I just want plain old y, right? So what do? I need to divide by negative 3, but just be careful, everything needs to get divided by negative 3. So we end up getting y equals 2 over 3x minus 7/3. So why do you notice, or what do you notice about this? Is this the most pleasant thing to really graph? The first equation was pretty easy, but the second one not as much, right? Because what's our y-intercept going to be? Negative 7/3, right, which is actually like negative 2.3333, okay? So we're just going to have to make do with it, and then we're going to talk about why sometimes the graphing method might not be as helpful. So plot your y-intercept at about negative 2.33, okay? If you didn't know that was negative 2.333, just plug it in your calculator. Negative 7 divided by 3, and it'll give you that. What is the slope telling you to do? It's telling you to... well, it was positive now, right? So we want to go up 2 and what? Up 2 into the right 3. Okay, so what did I do wrong on this one? The reason I'm saying that is because it's not looking like, where do we already know it's supposed to intersect? Like we already know the answer to this one, right? I pulled the same question. So, which one? Oh, yeah, that's it. Thank you. No, you're good. Yeah, so I knew something was up, right, because that wasn't going to be the right spot. So this should not be graphed. Our y-intercept is not negative 2.33. It's actually what? Positive 2.33. Okay, so good catch. So 2.33 is about here. That's going to look a lot better. Okay, so then notice we need to go up 2 and then over 3. Do you see that this is a little harder to tell maybe that it's perfectly where it's crossing? Particularly when the line is maybe a fraction. So here's equation 2. Okay, but I think my graph is good enough to kind of tell where they're crossing each other, right? So where does it look like they're crossing each other? Yeah, so basically they are intersecting at what? At the point 1, 3, which is what we got for the previous example. Okay, so the solution here is 1, 3. So if you're a more visual person, I think this is a good method for you to choose, but what do you notice as the drawbacks? Like, your graph's going to have to be decent, right? Like, it can't be just a thrown-up graph. It can't necessarily, you can use your graphing calculator a little bit to help you, but, I mean, you're going to have your details right, okay? Yes?
Do all methods always work?
Yes. Well, if there's a solution, all methods work. If they're parallel lines, then they never cross each other, and so you wouldn't get an answer in that case. Okay? But that's where the graphing method would be helpful. If you draw 2 parallel lines, you're going to be like, hey, they're never going to touch each other. So the answer would be no solution in that case. We won't really run into that scenario much since we're doing kind of real-life data that should have a solution. Okay, so we are going to talk about the fourth way, the matrices way, but I want to take a break from the 4 methods, and I want to look at some economics/business applications. So I want to talk about supply and demand, okay, because we can look at system of equations with supply and demand. Okay, so if you've had basic economics, then you can probably answer for me what these are. But if not, supply describes the price suppliers want to sell their item for. And demand, on the other hand, represents the price that what? That people are willing to pay, right? The consumers. So this describes the price consumers are willing to pay for a product. So I don't think it's hard to imagine that these quantities are often at odds with each other. Okay, what the suppliers want to sell a product for might not be the same thing that that consumers are willing to pay for a product. But what we're striving for in economics, whether or not we can actually achieve it, okay, the goal is for these things to be equal. Okay, because when they are equal, we're at a state called equilibrium. Okay, the goal in economics is for all the items that a producer makes to get sold and for everybody to be satisfied. Everyone who wanted a product got to get one, basically. Okay. Now, in real life, do you think this happens all that often? That it's perfectly, like the suppliers sell out all their stock and nobody is lacking anyone, right? If that were the case, we wouldn't have things being sold for more than what they're worth on like eBay, right? eBay is created by the demand being higher than the supply is, right? So people are willing to pay more than probably they should for an item. Okay, so I think we've talked about these briefly this semester, but I just want to make sure we're clear. Remember, C of X is cost. Capital R of X, do we remember what that is? Revenue. And then we use capital P of X for profit. Remember I said capital P of X is profit, but we usually reserve lowercase p of x for price, okay? So based on what we said before, and what we know about cost, revenue, and price, a lot of times the break-even point in a business is something of interest to us. So this is basically the number of items. Remember that stands for number in math. The number of items needed for a company. What does it mean if a company breaks even? What do they profit exactly? Nothing, right? But what's the benefit to that nothing? Yeah, they don't lose money, right? But they're not to the point of making money yet. Okay? Most companies want to know where their break-even point is because then they know that after that, what should start happening? They should start making money at that point, right? So it's kind of implied, but I want to make sure. Break-even occurs when cost is exactly equal to revenue. Because, remember, profit is revenue minus cost. Okay, so let's look at maybe some of these economics examples. So let's say that a mower company has the following cost and revenue functions. So we want to know kind of what the recommendation for this business is if these are the very basic cost and revenue functions. Okay, so just to kind of recap before I ask you what I want you to solve on this, okay, what does it mean about the 48,000? What is 48,000 called? We kind of talked about it before. The fixed cost, right? How do we know that? Because that's being added no matter what, right? And then the 1,400 is what we know as the variable cost, right? What does it look like we're selling the mowers for? You should be able to look at this equation and tell that. 1,800, right? But we're not getting to pocket the 1,800 if we're the mower company owner. How come? What do we still have to pay before we actually get to decide what we pocket? We still have to pay the cost, right? So my question is, how many mowers need to be sold to break even? Okay. So one way to do this would be to graph both of these things and then find out where they cross each other, right? We want to know where they intersect. But why would graphing be a little difficult for this problem? The numbers are ginormous, right? Even on our graphing calculator, it's probably not going to be all that helpful, right? We're going to have to zoom way out. We're not going to get any detail on a graphing calculator. But we can set what equal to what. Yes, we can set cost equal to revenue. And then essentially we'll just have a pretty simple algebra equation to solve. So if I want to know what x is, I'm going to move my 1,400x over. So just make sure with numbers this big that if you need the help of a calculator that you use it. And then what would be my final step? Divide by 400. Okay, so if you use your calculator, you're going to get 120 mowers. Now, if we're the mower company, we're probably not satisfied with selling 120 mowers. Why? Why are we probably not satisfied with just selling 120? Yeah, you're not going to profit anything, but at least at this point, you know you're not losing money, right? Which happens in business until a certain point, right? So what would we know, for instance, if we sold 125 mowers? We'd know that we're somewhere in the profit, right? So we should be able to figure that out. If I asked you to figure that out, how could you do it, by the way? Okay, can't you? So let's maybe do a part B where I ask you to do that. So what if I ask you for the profit for selling 125 mowers? Okay, well, we know we're going to be in the positive, right? We know we're not going to be losing any money because we're past the break-even point. Okay, but so to do this, we're going to have to remember what our formula for profit is. Okay, and I already mentioned it today. What's the formula for profit again? Revenue minus cost. Okay, so just be careful when you subtract these that you use a parentheses because it's actually minus the entire cost equation. In other words, this minus sign actually needs to go to both. So we would actually get 1,800 x minus 48,000 minus 1,400 x, or 400 x minus 4,800. That actually should intuitively make sense to you, because essentially we're making the difference between the 1,800 and the 1,400 per mower, but then what are we still having to pay off? And I missed a zero there. We're still having to pay off that fixed cost of 48,000, right? So let's go ahead and plug that in then. So what are we going to plug in to our profit equation then? 125? And we'll know that we're on the right track if we get a positive answer, because we know we're supposed to. So we'll use our calculator, but we get 400 times 125 minus 48,000. And so it looks like we will profit $2,000. Okay. Now that you see that, what do you notice would be the pattern? If 5 extra mowers made us $2,000, what does it look like we're making per mower past the break-even point? Yeah, so we're making the extra 400 per one, right? So if we sold 10 extra mowers, we should make how much instead? 4,000 and so on. Okay, so sometimes you can kind of notice a pattern. Okay. Okay, so let's look at maybe an economics example here. So let's say that a company has a supply function of price equals, let's go with 7.95x plus 24,000. And a demand function of price equals 1995x and I want you to find the number of units sold to have equilibrium. What's the base word for equilibrium? Equal. Okay. Sorry, I keep running it off the page there. And apparently I really can't spell today. It's just a Monday for me, that's all I can say. Equilibrium, there we go. Okay, so let's kind of write it because I want you to be kind of used to this when you see this in economics. So the supply function is 7.95x plus 24,000. The demand function is simpler. Okay, 19.95x. So if I want to get equilibrium, I can kind of underline that prefix, right, which means equal. Okay, so what do I need to do with these two? Also notice that they're both equal to P. So if they're both equal to P, what do we know about them compared to each other? They're equal to each other, right? So we're going to set supply equal to demand. And we're going to solve from there. So 7.95x plus 24,000 equals 19.95x. So again, the graphing method would be a little ugly here. Okay, we wouldn't want to use the graphing method because the numbers are just a little too ugly. So let's subtract 7.95x. So we would get 24,000. And then we would get 12x, right? 19.95 minus 7.95 is 12. And then we'll divide both sides by 12. So we should get x equals 2,000. Make sure on word problems or application problems you label what you get. Okay, so it's 2,000 units that we would need to sell. 2,000 units would put us at perfect equilibrium where all the items would be sold, everybody would be happy. Okay, the producer would get rid of all their items and every consumer that wanted one would get one. Okay. So just remember, although we're striving for equilibrium in economics, what's the hard truth? You don't hit it very often, okay? Very, very, very rarely do you hit it, okay? But that doesn't mean we, quit trying, okay? Okay, so notice for all of these problems, I'm just asking you to use one of the methods. Notice this is essentially what kind of method? We talked about elimination, we talked about substitution, and we talked about graphing. So graphing's out on these kinds, right, because it's just too ugly. So what method are we really essentially using here? We're using substitution, yeah. It's just that we have them both equal to the same thing and we're setting them equal to each other, okay? But we're essentially using the substitution method. Okay, so next class, be ready to look at matrices, okay? So I just want to kind of get you ready for that. So next class, we're going to look at how to solve things using a matrix. And here is what a matrix can look like. You can put as many numbers as you want in a matrix. So one of our Microsoft Office programs essentially is a matrix. It just doesn't tell you. Which program seems to have numbers in rows and columns? Excel. Excel is a glorified matrix. That's all it is. But this is what we would call a 2x2 matrix, and this is what we would call a 3x3 matrix.
So do you not separate the numbers by commas?
You do not. No, not in a matrix. Like, you won't ever see that. Because it gets too tedious, okay? So just know that matrices can be bigger than this, okay? And that's actually where their benefit lies when you have a whole bunch of variables. We're going to stick with 2x2 and 3x3, okay? But just know that they can get actually a lot bigger than that. So if you take some upper-level finance/economics classes, you might do some matrix math that has more columns and rows than this. But you would be using a computer program at that point, so, I mean, it's a little less intimidating then. Yes?
Do they always have to be perfect squares, or
They do not.
so it could be 2, 3, or 4?
Yeah.
6,
Now, the ones we're going to look at are going to be a little more nice for the most part, but they do not have to be perfect. Yeah, they can be different numbers of rows and columns. Okay, and so think about like the benefit. So before we get into what we're doing next time, because I always have students really intimidated by matrices, okay? But I just want you to see like what's the benefit of Excel? Like it allows you to put like a whole bunch of numbers in rows and columns, and then it allows you to do like one formula and send it down the whole row or send it through the whole column, right? So that's the benefit of matrices. Also, we're going to learn how to do what's called matrix math, which just allows you to send kind of one operation all the way through it, okay? So they do look weird, and I get that they might be a little intimidating at first glance, but there's actually a lot of benefit to them, okay? So next time, prepare to kind of start talking about how we can manipulate these rows and columns in some way, okay? All right, so I will see y'all on Wednesday.